So today's lesson is going to be on solutions, where we have two main types of mixtures. A homogeneous mixture, where things are mixed evenly together. All right, and this would be an example of, say, like maybe a glass of salt water. All right, if you were to take a sip of salt water, which we should not do, I don't recommend that, but if you did, it would taste the same if you took another sip of salt water. It's mixed evenly throughout. Our second type is heterogeneous mixture, where we have an uneven mix. All right, and this would be like orange juice with pulp, for example. You may get more pulp in one sip than you do in another sip. So it's not mixed evenly throughout. Now, ultimately, our solutions in terms of homogeneous or heterogeneous are going to be determined by their intermolecular forces. A homogeneous mixture is going to be one where our substances have similar intermolecular forces. All right, and so we have this example down here. Gases, for example, have similar intermolecular forces because if you remember, we said that gases tend to behave as an ideal gas, and in an ideal gas, we say that intermolecular forces aren't there. So now we know that the intermolecular forces are there. They're just very similar, which is why we're able to have, like air, for example, where it's mixed evenly throughout. So you breathe air in the room you're in, and then you go into a different room and you breathe air, and you're still okay because it's mixed similar throughout, okay? The oxygen and the nitrogen and the water vapor and all of those substances in the air are evenly mixed. Our next example is sodium chloride, which we know will break apart into ions, and water, which we've learned is a dipole substance. It's a polar covalent, giving it a dipole as its intermolecular force. So the partial negative of the oxygen is attracted to the cation sodium, and the partial positive of the hydrogen from the water is attracted to the anion chloride, forming an ion dipole bond. This has a dipole, this is an ion. A heterogeneous mixture, substances have different intermolecular forces. For example, oil and water. Oil is nonpolar and water is polar, which is why when you mix oil and water, they don't mix well together. A couple of vocabulary terms that you're going to need to know. A colloid. A colloid is a type of heterogeneous mixture, and it displays the Tyndall effect, meaning it scatters light. For example, fog and milk are both colloids. And you learned in driver's ed that on a foggy day, you drive with your low beam lights on, never high, because fog is a colloid and it scatters the light. So when you are driving with high beams on, it actually scatters that light in a foggy situation such that it makes it very difficult to see. A suspension is another type of heterogeneous mixture, all right? And this is where we have large particles that are suspended within a substance, but if you allow them to sit, they will settle out, meaning the large particles will fall down to the bottom of that solution. And an example of that would be muddy water. The mud will fall down to the very bottom of the container. Some medications are also suspensions. So if you get a medication that tells you to shake well before use, chances are that medication is a suspension, and you need to shake well in order to mix it up so that you are getting the correct dose. Now, why does this matter? It matters in terms of solubility. All right, and we've already looked at our solubility rules and determined things that can and cannot dissolve, all right? Solubility is defined as the amount of solute that can dissolve in a specific amount of solvent, where the solute is what is getting dissolved, the solvent is what is doing the dissolving. Now, solutes tend to be solids, but they are not always. It could be a liquid or a gas, but typically they are a solid in this class. When we dissolve a solute in a solvent, we have three types of solutions: unsaturated, saturated, and supersaturated, where unsaturated has less than the amount that the solution can hold. So we could actually get more to dissolve in. And if we were to look at a solubility curve where we look at the solubility based on temperature, an unsaturated solution would be underneath the line. So I'm going to just do some color coding here. Unsaturated. Okay. A saturated solution is a solution where we have the maximum amount of solute that can be held. We cannot add any more. And let me make this green. So when we look at a solubility curve, the line itself is the point of saturation, where we say a solution is saturated. A supersaturated solution is one where we have more solute dissolved than we should be able to hold. And these are typically made by heating, all right? Because when you heat, as we add temperature here, we increase the temperature. As we add heat, we see the solubility typically tends to increase. And these are things for like ionic compounds that are solids. All right, so supersaturated, if we were to heat, that is going to be above the line. So let's look at a couple of practice examples here to see if we can't make all of this make sense. Now this comes from your worksheet, which I have placed onto the website, your student website. All right, and we're going to be using our solubility curve. And what do we notice here? The overwhelming majority of these different substances are increasing in solubility as the temperature goes up. We do have some substances which are decreasing, all right? And when we see a decrease as temperature goes up, so as solubility decreases as temperature goes up, those are gases. All right, so gases, as we increase temperature, we see a decrease in solubility. For solids, as temperature goes up, we see an increase in solubility. Now let's look at some practice examples. Notice our solubility curve. This is the grams of solute per 100 grams of water. So water is the solvent. The solute is whichever substance we are looking at. So this line right here would be sodium nitrate, for example. So what is the mass of solute will dissolve when we are at what temperature? So part A, potassium nitrate at 70 degrees. So what this is asking us to do is to find the point of saturation. So I'm going to take 70 and I'm going to go all the way up to my potassium nitrate line, which is right here. And I'm simply going to read over, and I see it's just under the 130. So since it's just under the 130, I would say maybe 129 grams. Now, if you read it as, say, 130 grams, that would be fine. There is some interpretation within these graphs. All right, so where's sodium chloride saturated at 100 degrees? So I have 100 degrees. Here is my sodium chloride line. All right, 100 degrees. My sodium chloride line is at exactly 40 grams. All right, where is ammonium chloride saturated at 90 degrees Celsius? So 90 degrees, we're going to come up to our ammonium chloride line, and we see that its point of saturation is at 70. So I could get 70 grams of ammonium chloride to dissolve in 100 grams of water at 90 degrees Celsius. So which of the above three substances is most soluble? So we were working on this problem 1D. Which of the above three substances is most soluble in water at 15 degrees Celsius? So I have to look here at my solubility curve, and at 15 degrees Celsius, I'm going to find my sodium chloride, which is right here, my ammonium chloride, which is right below sodium chloride, and my potassium nitrate, which is right here. So I see out of these three substances that my sodium chloride, in fact, is able to be the most soluble at 15 degrees Celsius. All right, number 2, at 80 degrees Celsius, 40 grams of potassium chlorate is dissolved in 100 grams of water. If the temperature is decreased to 40, how much potassium chlorate will precipitate out? All right, so what I'm going to do is I am going to find the point of saturation at 80 degrees Celsius first, and then I'm going to find the point of saturation at 40 degrees, and I can subtract out the difference to figure out how much precipitates out. So potassium chlorate. All right, so potassium chlorate at 80 degrees is able to hold 40 grams. And at, what was my temperature? 40 degrees Celsius, it is able to hold somewhere around 15 grams. So if I am able to hold 40 grams at 80 and only 15 at my next temperature, that means 25 grams will precipitate out. How much sodium nitrate must be added to make 50 mils of a saturated solution at 10 degrees Celsius? All right, now we have to notice here, we want 50 milliliters. And remember, the density of water is 1 gram per milliliter. So 100 grams is essentially 100 mils. So here, 50 mils is essentially 50 grams. My chart is per 100, so I'm going to have to set up a ratio. All right, at 10 degrees Celsius, my solution of sodium nitrate can hold, let's see here, 10 grams. My solution can hold 80. All right, right here. So I can get 80 per 100. But my problem asked me for 50. So I simply solve for x. Two ways you could solve. You could do 80 divided by 100 equals x over 50 and then multiply, or you can cross multiply, where you get 80 times 50 equals 100x. 80 times 50 equals 100x. And when you solve for x here, you find x to be 40 grams.